My students always ask me great questions, but from time to time a student will ask something so brilliant that it gets my creative juices flowing. Last week, one of my students said to me, "How come you just can't keep on adding more and more neutrons? After all," he said, "they are the glue that holds everything together." That was such a brilliant question that it sent me down a rabbit hole, and that's the subject of this simplified video. It might seem fairly logical that given you have a stable nucleus and you try to add in more protons, that the additional repulsive Coulomb forces that you're adding into that nucleus would cause it to become unstable. On the other hand, you might think that if you add in neutral neutrons, because you are not adding any more repulsive Coulomb force to the nucleus, but you are in fact adding in additional strong attractive nuclear force, that this will be a good thing because you're giving more glue to the structure, holding the nucleus together more strongly. In fact, of course, it's not that straightforward, as a quick inspection of the nuclear stability graph, which shows the number of protons along the x-axis and the number of neutrons up the y-axis, will clearly show you. So there's obviously something else going on. As you'd expect with all things physics, what we're going to do is peel off another layer of skin on the onion. We never seem to get to the bottom of anything, do we? This is Wolfgang Pauli, and one of his most famous contributions is something known as the Pauli exclusion principle. By now you probably know that subatomic particles can be divided down into lots of different families. One that you probably haven't heard of is fermions, and it turns out that protons and neutrons, and electrons too, are all fermions. The principle states then that no two identical particles, e.g. two protons, can occupy the same quantum state. A quantum state is a set of numbers or properties that can be used to describe a particle. These include things like intrinsic angular momentum, spin, or energy. Yes, it is getting complicated now, but do not despair because you've met something just like this, if not by name, in principle. Have you ever wondered why it is that electrons fill up the energy levels with the magic numbers 2, 8, 8? This is because of Pauli's exclusion principle. What this means then is that the protons and neutrons behave in a somewhat similar way to the electrons in shells, in that they can only exist in certain predefined states. Think of it like a row of chairs that you have to fill up from one end. So if the first 6 chairs are taken, you can't sit in them, can you? Because somebody's already there. At this point, our simple chair analogy breaks down. So let's consider instead 2 simple cylinders which we can fill with protons in one, neutrons in the other from the bottom. Naturally enough, as you add protons and neutrons, they will go to the bottom of these cylinders, which represents lower energy states. And as we fill, we find they are in higher energy states. Let's build the nucleus A equals 16. There are different combinations of protons and neutrons that we could use to make A equals 16, but let's start with the obvious one, 8 protons and 8 neutrons. As we build this version of A equals 16, it's clear that both columns will have the same number of levels. This means that there is no difference between the energy of the proton pool and the neutron pool, so everything is nicely balanced. Now let's build our A equals 16 nucleus with 6 protons and 10 neutrons. Given that the higher up the column, the higher the energy the particle has, we can see now that our A equals 16 nucleus has considerably more energy than it needs to have. What if we could find a way to move some of those high energy neutrons into the lower but available energy states for the proton column? Doing so will significantly decrease the overall energy of this A equals 16 nucleus. Pauli's exclusion principle clearly plays a part in the nuclear stability conversation. However, it is one of a number of factors that contribute to the stable ratios of N to Z. Therefore, it is not the whole story. If you would like to know a little more about this, try researching the liquid drop model. Yes, you'll come across some horrific maths, but ultimately, this will give you a clearer understanding of some of the other factors. If you'd like to see a simple explanation of how the nuclear strong force works, check out this video.